Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome, everyone, to what I think is a truly awe-inspiring journey we're taking today, right into the heart of the cosmos.
Definitely.
Tonight, we're not just looking at the stars you see. We're going to zoom out, way out, far beyond what our eyes or even, our best telescopes can really show us. We want to see the universe's true skeleton. Imagine, if you can, uncovering this immense, sprawling architecture that basically dictates where everything is.
And where it isn't.
Exactly. Across distances that they defy comprehension, don't they?
They absolutely do.
That's precisely what we're here to explore. This mind-bending reality of the cosmic web. That's the structure of our universe. And it's a challenge for scientists of, unimaginable scale and complexity. How do you even start to make sense of something so vast, so intricate, and so ancient?
Right. It sounds like science fiction almost.
It really does. But it's very real. And thanks to some cutting-edge tools, we're actually getting closer to mapping it than ever before.
And that's exactly our mission in this deep dive. We're going to reveal how an international team of scientists has developed, a truly revolutionary shortcut to do just that.
A shortcut. Okay. I'm intrigued.
Yeah. They built this ultra-fast emulator. It's dubbed Effort.jl. And it's capable of mapping the universe much faster and with incredible detail.
Wow.
And this isn't just about, speeding up research. It's really about unlocking some of the deepest secrets of cosmic evolution itself.
Okay.
So we'll explore not just what this emulator does and how it works, but critically, why it matters so profoundly for the future of cosmology. And for our understanding of everything around us, really, from the smallest particles to the biggest structures out there.
Okay, let's unpack this scale first, because it's mind-bending, right? When we talk about the universe, our brains, they kind of default to things we can grasp, like the size of Earth, maybe the solar system.
Sure, familiar scales.
Yep. But what we're talking about here, it's just a whole different level, a different magnitude entirely. You look up at the night sky, you see galaxies, those magnificent swirls, billions of stars. They seem enormous to us, unfathomably large.
Just a universe unto itself, almost.
Exactly. But in the grand scheme, a galaxy, even our own Milky Way, it's basically nothing more than a tiny speck, an almost microscopic dot.
Right. Hard to internalize that scale.
It really is. Just one of countless tiny dots scattered across this unimaginable expanse. And crucially, these dots, they don't just float randomly, do they?
No, not at all. Gravity plays a huge role.
Right. They have this profound tendency to aggregate, to clump together under that relentless pull of gravity. We see them forming these immense collections called clusters.
Hundreds, sometimes thousands of galaxies together.
Yeah. And then, as if that wasn't big enough, these clusters aren't isolated either. They then aggregate into even larger structures. Scientists call them superclusters. Our own Milky Way, for instance, it's part of the local group, which is itself sort of on the outskirts of the Virgo supercluster.
Which is part of Laniakea.
Exactly. Laniakea's supercluster. The scale just keeps ballooning outwards. It's incredible.
It keeps going.
But the aggregation doesn't stop there, does it? And this is where the picture really starts to come into focus.
This is the cosmic web itself.
Yeah. All these clusters and superclusters, they aren't just scattered randomly in space. They're woven together into this immense interconnected network, like a colossal cosmic spider web.
That's a great analogy.
This is the cosmic web, this incredible three-dimensional skeleton of the universe. It's characterized by these long thread-like structures, filaments they call them.
Filaments, yes. That's where galaxies tend to cluster, along these sort of cosmic highways.
And these filaments can stretch for hundreds of millions of light years, forming the densest regions. And then between these filaments, you find these immense, almost completely empty regions called voids.
Vast voids, yeah. Hundreds of millions of light years across, often with very few galaxies, if any.
So it's in these filaments that most of the visible stuff, the observable matter in the universe is concentrated, giving the universe its fundamental large-scale structure.
Yeah, what's truly fascinating here is just how difficult it is for our intuition, for us humans, to really grasp structures this immense, and maybe more importantly, how they even formed.
Right, the formation process.
We're talking about scales that just dwarf anything we experience day to day. And the cosmic web isn't just like a static picture, a snapshot frozen in time.
It evolved.
Exactly. It's the culmination of billions of years of cosmic evolution, driven primarily by gravity. To really get this, you have to step back, way back to the dawn of the universe.
Okay, near the Big Bang.
Right after the Big Bang.
Yeah.
Imagine the universe then, this hot, dense, nearly uniform soup of particles. But nearly is the key word there.
Not perfectly uniform.
No. There were these infinitesimal quantum fluctuations in density, tiny, tiny ripples in this cosmic ocean. So small they were imperceptible at first.
Right.
But over billions of years, gravity began to relentlessly amplify these tiny ripples. And here's where the mysterious dark matter plays its huge, unseen, foundational role.
Dark matter, the invisible stuff.
Exactly. It doesn't interact with light, but it has immense gravitational pull. And it started to clump together first. Because it doesn't interact with light or normal matter in the same way, it collapsed more efficiently, forming this invisible scaffolding or skeleton throughout the early universe.
So dark matter laid the groundwork.
Pretty much. Normal matter, the stuff that forms stars, planets, then gradually fell into these gravitational wells created by the dark matter. It essentially traced out this underlying structure.
Like following a blueprint.
Yeah, like an invisible blueprint forms first, and then the luminous flesh of the universe kind of coalesces around it. So it's gravity that dictated where matter is, and crucially, where it isn't. These structures are the direct consequence of the universe's initial conditions, its expansion, its evolution. It basically tells the whole story from the Big Bang onwards.
And that's exactly the central, just mind-boggling question scientists face, isn't it?
Yeah.
How do you even begin to see this, or study it, or truly understand something so vast, so intricate, so ancient?
Especially when it's sculpted mainly by invisible dark matter.
Right. Spanning nearly the entire observable universe. How do we map its fundamental properties, measure how it evolved over cosmic time, uncover the precise physics governing it all? It's not like we can just, send a probe out there to take pictures of the whole thing.
Definitely not feasible.
So this monumental challenge, it's driven scientists to develop some incredibly sophisticated methods, combining meticulous observation with deep theoretical insight. Which, I guess, leads us to our next major point.
Precisely. To tackle this, the traditional and still incredibly powerful scientific approach involves theoretical models. Specifically, one of the most successful and robust frameworks for understanding the large-scale structure is called EFTofLSS.
EFTofLSS.
Okay, it stands for the effective field theory of large-scale structure. Its fundamental purpose is to provide a comprehensive, rigorous description of the cosmic web.
How does it do that?
It does this by combining the known physics of the universe, everything from, say, general relativity's influence on gravity, to the properties of the fundamental particles making up matter and energy. It combines all that with the vast amounts of observational data we gather from astronomical instruments, telescopes, sky surveys, things like that.
Okay, so it blends theory and observation.
Exactly. Now, how do these models work? Well, rather than trying to track every single particle or even every single galaxy individually, which would be utterly impossible, just think of the numbers involved.
Like mapping every grain of sand on Earth.
Right, exactly that kind of impossible scale. Instead, EFTofLSS describes the cosmic web statistically. It focuses on the collective behavior, the distribution of matter on very large scales. It averages out the messy, complex details of individual galaxies or small clusters.
So it looks at the big picture trends.
Precisely. And by feeding these models with real observations, scientists can then estimate the key cosmological parameters that define the cosmic web structure.
Parameters like?
Things like the total density of matter and dark energy in the universe, the initial amplitude of those tiny fluctuations we talked about earlier, the rate the universe is expanding, things like that.
Gotcha.
And by pinning down these parameters, EFTofLSS lets us gain crucial insights into how the cosmic web formed, how it evolved, and the underlying cosmological principles that govern it all.
Okay, here's where it gets really interesting, but also maybe a little abstract for those of us who aren't theoretical physicists, right? Effective field theory of large-scale structure. It sounds incredibly complex.
It is complex, yeah.
For listeners who aren't steeped in this stuff, how can we really grasp what this theory does? How does it simplify such immense complexity without losing the essential truth? Is there like a way to picture it? an analogy, maybe.
Absolutely. And actually, Marco Benici, one of the lead researchers on the Effort.jl study we'll get to, he offers a fantastic analogy that really helps make EFTofLSS more comprehensible.
Right. Let's hear it.
Okay. Imagine you're trying to study a glass of water, specifically how it moves when you stir it or pour it.
Right.
Now, in theory, you could try to describe the water's movement by tracking every single individual atom, or even the subatomic particles within them. That's the microscopic level.
Okay, but that sounds impossible.
Well, if you wanted to accurately describe what happens when the water moves, trying to calculate the interactions of countless trillions of atoms, it leads to this explosive growth of calculations. It would be practically, if not theoretically, impossible to simulate even a few seconds of fluid movement at that fundamental atomic scale.
Right. Too much information.
Exactly. So instead, what you do is you encode certain properties at the microscopic level. You understand atoms have mass, they attract each other, they collide, they have kinetic energy, etc. And then you observe their effect at the macroscopic level.
The big picture.
Right. That macroscopic effect is the fluid's movement itself. You describe the water's flow using concepts like pressure, density, viscosity. These things emerge from those underlying atomic interactions, but you don't need to know the exact position and velocity of every single molecule. You've effectively distilled the essential large-scale behavior.
Okay, that makes sense. You capture the overall flow without tracking every drop.
Precisely. Now, draw the direct parallel to the universe. The water in this example is the universe on very large scales, the cosmic web itself. The microscopic components are the small-scale physical processes that influence that large-scale structure. This includes things like, the formation of individual galaxies, the incredibly complex dynamics within dense galaxy clusters, or the intricate behavior of gas and stars. Phenomena that are just far too complex to simulate directly across the entire cosmos if you want to understand the entire web.
Too much detail again.
Right. So EFTofLSS steps in to effectively describe how these small-scale processes collectively influence the large-scale cosmic web, those filaments and voids, without needing to model every single tiny detail. It's about capturing the essential physics that shapes the universe on its grandest scales, providing a statistically accurate and predictive model.
That analogy really helps distill the elegance and the power of EFTofLSS. It sounds incredibly effective, allowing scientists to make such headway in understanding the universe's grand design.
It is very powerful, theoretically.
But despite its theoretical beauty, I imagine applying it to the universe's full scope, especially now with this explosion of new data we keep hearing about, presents some very tangible, very demanding challenges, doesn't it?
Oh, absolutely.
So what does this all mean for actually using these models, for processing the vast amounts of information we're collecting? Your analogy hinted at the computational challenge. Tracking every atom is impossible. Does that mean applying EFTofLSS to the whole universe, even statistically, still demands a lot of time and computing resources?
It absolutely does. And this is exactly where the theoretical elegance meets a very real, very practical bottleneck. While EFTofLSS is a powerful theoretical framework, applying it directly, exhaustively, to real astronomical data is incredibly resource-intensive.
How intensive?
Well, each calculation, each prediction from the model requires significant computational horsepower, often needing supercomputers running for days, sometimes even weeks, just to produce a single result.
Wow, days or weeks for one run.
Yeah. And here's the core problem. The astronomical datasets we have now aren't just growing, they're growing exponentially at a truly staggering rate. We are really entering a golden age of observational cosmology. We're collecting more information about the universe than ever before.
Like the new surveys.
Exactly. Think about monumental efforts like DSI, the Dark Energy Spectroscopic Instrument. It's already started releasing its first data batches, mapping the positions of tens of millions of galaxies and quasars across a huge chunk of the universe.
Tens of millions.
And its main goal is to precisely measure the expansion history of the universe to understand dark energy. Then there's Euclid, the European Space Agency's mission. It's coming online soon.
What will Euclid do?
Euclid promises to deliver an unprecedented volume of highly detailed data about the universe's large-scale structure. It'll probe dark energy and dark matter by measuring the shapes and redshifts of over 1 billion galaxies across billions of light years.
1 billion galaxies. The data volumes must be immense.
They are. Petabytes of data. So much information that our traditional analytical methods, even with sophisticated models like EFTofLSS, they just struggle to keep up.
Right.
It becomes practically impossible to do an exhaustive analysis, testing every possible parameter combination, every scenario, every time you want to check a hypothesis against this flood of new data.
You need those supercomputers running constantly.
For weeks or months for each iteration, and that's just not practical for the iterative, explorative nature of science, especially with such huge data volumes. This computational barrier is a critical challenge. It necessitates a radically new approach.
And that necessity, that computational bottleneck you just described, brings us directly to, well, a crucial answer that's transforming cosmology, the rise of emulators.
Exactly.
If our traditional models, powerful as they are just too slow to keep pace with this data deluge, then we need something faster. You used the word shortcut earlier, and that's essentially what an emulator is, isn't it?
In a sense, yes. A very sophisticated shortcut.
So a simple definition might be that emulators imitate how the full, complex theoretical models respond to different inputs. But crucially, they operate much faster.
Much, much faster.
So instead of running that super intensive full model every single time you need a result, you have this high fidelity stand-in, this digital doppelganger. That gives you essentially the same answer, but almost instantly.
That's the goal, yes. High fidelity is key.
And this is absolutely critical given today's data volume and what we expect from future surveys like DSI and Euclid. As you just explained, it's simply not practical to do this exhaustively every time with the traditional methods. Emulators are becoming not just useful, but truly indispensable for modern cosmology.
They really are. And to dive a bit deeper into the mechanism, what's fascinating here is that at its heart, an emulator is typically powered by a neural network.
AI machine learning.
Exactly. This is where machine learning comes into play. Now, the neural network isn't explicitly programmed with the physics equations of the universe in the same way EFTofLSS is. Instead, it learns from examples.
Yeah.
Much like a student learns from practice problems.
Okay, how does it learn?
Well, the training process works like this. Scientists first run the full, complex theoretical model, like EFTofLSS, a carefully selected number of times, using various combinations of input parameters.
The parameters we talked about before, like matter density.
Right. Things like matter density, dark energy amount, the initial fluctuation properties, expansion rate, and so on. For each set of inputs, the full model produces a prediction or an output, maybe a statistic about galaxy clustering or matter distribution.
Okay.
The neural network then learns to associate these input parameters with the model's already computed predictions. It builds an internal mathematical representation of this complex relationship between inputs and outputs. It finds the patterns.
So it learns the input-output map.
Exactly. After this intensive training phase, which might take a significant amount of computing time itself, mind you, the neural network, now functioning as an emulator, can generalize to combinations of parameters it hasn't seen.
So it can predict new scenarios.
Yes. If you give it a new set of cosmological parameters it wasn't explicitly trained on, it can quickly and accurately predict what the full theoretical model would have outputted.
That's powerful.
It is. But there's a crucial distinction, though. The emulator doesn't understand the physics itself, not in the way a human physicist does, or the way EFTofLSS explicitly encodes it.
It just knows the pattern.
Right. It knows the theoretical model's responses very well and can anticipate what it would output for a new input, based on the patterns and relationships it learned during training. It's like a highly skilled mimic, reproducing the results without necessarily comprehending the underlying process.
That makes a lot of sense. It learns the relationship, the pattern, rather than solving the equations directly, and that's incredibly powerful for speed. But, okay, since this is a kind of shortcut, an imitation, it raises a really critical, intuitive question listeners might have. What's the risk of losing accuracy? Are we sacrificing precision for speed?
That's the million-dollar question, isn't it?
Because when we're talking about mapping the universe, good enough isn't really good enough, is it? We need it to be fundamentally correct, scientifically robust.
Absolutely. And that's a completely valid and crucial concern. It's one that the developers of these emulators spend a huge amount of effort addressing. The whole point of these advanced emulators is precisely to lighten the analysis without losing precision.
Okay.
It's not about cutting corners in the science. It's about finding a computationally efficient way to arrive at the same high-precision answers that the full theoretical models would provide. Rigorous validation of this precision is paramount. Scientists simply cannot accept a tool that gives faster answers if those answers are wrong or less precise.
So validation is key.
Absolutely.
Okay.
And this commitment to accuracy is a key part of the groundbreaking work we're diving into today, as it's been robustly demonstrated.
And that brings us seamlessly to the specific groundbreaking emulator that's really at the heart of this deep dive. Effort.jl.
Yes, Effort.jl.
This isn't just a theoretical concept or some lab experiment. It's a real published tool making significant waves in the cosmology community right now.
It really is.
It was developed through a truly collaborative effort, wasn't it? An international team, researchers from INEF in Italy, the University of Parma, also Italy, and the University of Waterloo in Canada.
That's right, a strong collaboration.
And their work, titled Effort.jl, a fast and differentiable emulator for the effective field theory of the large-scale structure of the universe, was published in the Journal of Cosmology and Astroparticle Physics, a top journal.
Indeed. So stepping back, the broader significance of Effort.jl lies in its primary game-changing achievements, which really speak to that balance of speed and precision we were just talking about.
Okay, what are the highlights?
First and foremost, it delivers essentially the same correctness as the full, complex EFTofLSS model it imitates. This is critical. It means that the shortcut doesn't compromise the scientific integrity or the precision of the results.
Same accuracy? That's huge.
It is. What's even more impressive, perhaps, is that in some scenarios, it actually achieves finer detail than the original model could manage in a practical time frame.
Finer detail. How so?
Well, for instance, when trying to model the intricate gravitational dance within a really dense galaxy cluster, or the precise distribution of matter within a cosmic filament, traditional EFTofLSS might have had to average over certain small-scale interactions, or use approximations, just to keep the computation feasible.
To save time.
Exactly. But Effort.jl's efficiency means we can now potentially probe those substructure details more effectively, offering a more complete, more nuanced picture. It might even reveal subtle signatures of, say, dark matter distribution that were previously smoothed out or averaged over.
Wow. So potentially more detail in some cases.
Potentially, yes, because the computational cost is so much lower. But perhaps the most dramatic achievement, the one that truly transforms the pace and, frankly, the accessibility of research, is the staggering speed up.
How fast are we talking?
Effort.jl runs in minutes on a standard laptop instead of requiring weeks or months on a supercomputer.
Minutes on a laptop compared to weeks or months on a supercomputer.
That's the difference, yes. Think about the implications of that. Cosmological calculations that once required access to massive, expensive supercomputing clusters took enormous amounts of time and energy.
Yeah.
Can now be performed in a tiny fraction of that time on hardware that's far more accessible to individual researchers, smaller institutions, even students.
That's democratizing, isn't it?
It really is. It democratizes access to high-fidelity cosmological analysis and dramatically accelerates the cycle of hypothesis testing, exploration, and discovery.
That's an incredible jump in efficiency. Minutes versus months? It's a game changer. Okay, let's unpack this. What exactly is the secret sauce here behind Effort.jl's efficiency and its accuracy? Other emulators exist, right?
Yes, other emulators are being developed and used.
So what are the unique aspects, the specific innovations that let Effort.jl achieve such remarkable results? Not just faster, but also potentially with finer detail. It can't just be like a faster neural network chip, can it?
No, you're absolutely right. It's not just about raw computational speed. It's about smarter, more informed learning. Effort.jl has a couple of key innovations that really set it apart.
Okay, what's the first one?
The first is how it achieves a reduced training phase through prior knowledge. Most neural networks, when you train them as emulators, they start almost from scratch, effectively trying to learn every single relationship and pattern just from the data they're fed.
A blank slate, sort of.
Kind of, yeah. But with Effort.jl, the team built in knowledge we already have about how predictions change when parameters change. Knowledge taken directly from the fundamental physics involved.
So they gave it a head start.
Exactly. Instead of making the network relearn these fundamental relationships, which we already understand pretty well from general relativity or cosmic expansion physics effort, .jl incorporates them from the very beginning. It's like giving a student, say, the fundamental theorems of calculus, instead of making them rediscover it all from scratch.
That makes sense. Saves time.
It significantly speeds up the training process because the network doesn't have to waste time and resources figuring out basic physical dependencies. It can focus its learning power on the more complex, more nuanced aspects of the model.
Okay, that's clever. What's the second innovation?
The second involves leveraging something called gradients.
Gradients, like on a hill?
Sort of. In this context, gradients tell us how much and in which direction the predictions change if you make just a tiny tweak to an input parameter.
Okay. How does that help?
Think of it this way. A neural network, when it's learning, is like a sculptor trying to create a perfect model. Gradients act as precise feedback. They tell the sculptor exactly which chisel stroke to make and how much pressure to apply to improve the model most efficiently.
Targeted improvement.
Exactly. Instead of just randomly chipping away, it has a precise, mathematically guided direction to refine its internal parameters, the weights and biases inside the network, to better match the known physics or the training data. And this capability to efficiently calculate these gradients, this direction of change, is what makes Effort.jl a differentiable emulator.
Differentiable.
Yeah, in simple terms, differentiable means its internal functions allow us to precisely measure how sensitive its outputs are to small changes in its inputs. And that's absolutely crucial for optimizing how it learns and ensuring its accuracy with less training data.
So it learns more from each example.
Precisely. It allows it to learn from far fewer examples during its training phase, because it's getting more information from each example, not just the output value, but how sensitive that output is to small changes in the inputs. It can train much more effectively with less data overall.
And that further cuts down the compute needs.
Exactly, which is precisely why it can run on smaller machines like a standard laptop. It's a very elegant and efficient way to teach the emulator the complex behavior of the universe, or rather, the complex behavior of the model simulating the universe.
Okay, that makes the speed and efficiency much clearer. But it brings us back to that validation point, doesn't it?
It certainly does. This raises that important question again. If the emulator doesn't know the physics in the traditional sense, if it's basically this highly sophisticated mimic, how can scientists be absolutely sure that its shortcut yields truly correct answers? Answers identical to what the full theoretical model would provide. This is where rigorous validation comes in. It's a non-negotiable step for any tool like this, aiming for real scientific discovery.
So how is Effort.jl validated?
Well, the newly published study provides exactly this extensive validation. The researchers didn't just build it, they put Effort.jl through its paces, an exhaustive battery of tests, rigorously testing its accuracy against the gold standard, the full EFTofLSS model.
What kind of tests?
They did this on both simulated data, basically, artificial universes, created in computers where you know the properties exactly, allowing for direct comparison, and crucially, they also tested it on real data from actual astronomical observations. Just like the kind coming from DSI.
And the results.
The results were conclusive. Effort.jl's accuracy across these diverse and demanding tests was found to be in close agreement with the model.
Close agreement.
Which means scientists can trust its predictions to be as reliable as those from the full, computationally intensive EFTofLSS model. But with that vastly improved speed, the agreement isn't just close. Often it's indistinguishable within the scientific uncertainties we normally work with.
That's a huge reassurance, knowing the accuracy is so rigorously validated. And it brings to mind that fantastic concluding remark from Marco Benici mentioned earlier. He said, and in some cases where with the model you have to trim part of the analysis to speed things up, with Effort.jl we were able to include those missing pieces as well.
Exactly.
That's not just as good as, that sounds like it's potentially better than using the original full model in practice sometimes.
That's precisely right. And it underscores a really profound, often overlooked benefit of these efficient emulators. What Benici's highlighting there is that with the full theoretical model, because it's so computationally demanding, scientists often face this difficult choice.
Compromise.
Yeah. Either spend an enormous amount of time and resources that they simply might not have, or they have to trim part of the analysis. This trimming might involve making simplifying assumptions, maybe focusing on a narrower range of parameters, or even ignoring certain subtle effects.
Like what kind of effects?
Perhaps some nonlinear gravitational effects that become important on smaller scales, or the detailed influence of baryonic physics that's the behavior of normal matter like gas and stars, which is super complex. They might simplify these things just to make the calculation tractable within a reasonable time frame.
Okay.
But Effort.jl's incredible speed and efficiency mean that these compromises are often no longer necessary. It can actually enable more complete analyses. By effectively removing that computational bottleneck, scientists are freer to explore the full complexity of the problem, including those missing pieces that might have been simplified or excluded before.
So it lets them be more thorough.
Exactly. It means Effort.jl isn't just a tool that's as good or faster. It actively enhances our ability to conduct more thorough, more comprehensive, and ultimately more accurate investigations into the universe's structure and evolution. It expands the very scope of what's even possible in cosmological research. It lets us ask more nuanced questions.
So what does this all mean for the future of cosmology then? If Effort.jl can deliver such accurate and even more complete results so quickly, it seems like a genuine game changer, especially for making sense of these huge volumes of data coming from current and future surveys. You mentioned DSI and Euclid again.
Yes, they are prime examples.
It sounds like Effort.jl isn't just some neat trick or a specialized tool. It's poised to become an indispensable, valuable ally for analyzing these upcoming data releases.
I think that's a fair assessment.
We're talking petabytes of information that will reveal the universe in unprecedented detail, from dark matter distribution to the subtle imprints of dark energy. Without tools like Effort.jl, researchers may literally drown in data, right? Unable to extract the scientific insights hidden within.
That's a real risk, yeah. Data overload.
This kind of computational tool seems absolutely essential for making sense of it all. It holds the promise to greatly deepen our knowledge of the universe on large scales, truly opening new windows into the cosmos. Imagine how much faster we'll be able to confirm or refute theories about dark energy, or precisely constrain the properties of dark matter. How quickly we can iterate on our understanding of the universe's origin and evolution. It feels like a leap in our capacity for discovery.
Absolutely. The profound impact of computational advances like Effort.jl on our ability to conduct cutting-edge research really cannot be overstated. These tools transform analyses that were previously either impossible or just prohibitively time-consuming into, well, almost routine tasks.
Making the impossible possible.
Pretty much. This isn't merely an incremental improvement. It's a fundamental acceleration of discovery itself. It allows researchers to explore vast parameter spaces they couldn't realistically touch before, test more complex and sophisticated hypotheses, and react much more quickly to new observational data as it comes in.
Faster iteration.
Exactly. I remember conversations, in the lab just a few years ago where we joke about how long it would take to run certain simulations, knowing they might not even finish within the lifetime of our research grants. Effort.jl and similar emulators are, thankfully, starting to make those kinds of computational bottlenecks obsolete. And this means faster insights into everything from the nature of dark energy and dark matter to the fundamental properties of the universe itself. It allows us to process the universe's autobiography, written in light and gravity at a speed we've never before imagined.
And that, I think, wraps up our deep dive today. What an incredible journey we've taken from just trying to grasp the mind-boggling scale of the cosmic web.
An immense 3D skeleton.
Filaments and voids, shaped mostly by invisible dark matter. Then, through the powerful theoretical models like EFTofLSS designed to understand it. And finally, to these revolutionary AI-powered emulators like Effort.jl.
Yeah.
Tools that are now supercharging our ability to map and comprehend the universe faster and with greater detail than ever before. It's really a testament to human ingenuity, isn't it?
It truly is. Collaboration and innovation working together.
For you, our listener, this story really highlights how gaining knowledge quickly and effectively, even for the most complex cosmic topics, is made possible through brilliant scientific thought, international collaboration, and the cutting-edge application of technology like AI. It's about finding smarter ways to ask bigger questions.
And then finding even smarter ways to get those answers.
Exactly.
Yeah, and looking at the broader implications. These computational shortcuts, they aren't just about raw speed. They're fundamentally changing what questions we can even ask about the universe.
Pushing the boundaries.
Exactly. By removing that bottleneck of computational power, they are pushing the boundaries of what's observable, what's discoverable, allowing us to explore the cosmos in ways that were genuinely unimaginable just a few years ago.
So a final thought then.
Yeah, the provocative thought I'd leave you with is this. What other scientific fields currently facing their own overwhelming data deluge, maybe think about climate modeling or drug discovery or material science, could similarly benefit from these emulation approaches? Where else could these techniques unlock their own deep dives into the unknown? The possibilities really are potentially as vast as the cosmic web itself.